My guest today is Jim Steele.
I'm an ecologist, and now was honored to be part of the CO2 Coalition's board. But I started off as being a strong environmentalist, and when people were blaming climate change when it was other reasons, I became very skeptical. So my thinking of how best to protect the environment is changed in terms of finding that there's a lot of hoax going on with this climate change stuff. So, I can tell you what's bothering me now and have a little presentation. What I call zonerisms are really manipulating the public. And what a zonerism is, it's defined as using a fact to lead scientifically ignorant public to a false conclusion. And it was named after Nathan Zoner in 1997. He was a 14-year-old ninth grader, had a science project titled, How Gullible Are We? And what he got was 43 out of 50 ninth graders to sign a petition to ban dihydrogen monoxide, otherwise known as water. And that you have this ninth grader that can fool that many people. And most of the public doesn't have a scientific background. So you change a word just from water to dihydrogen, often it throws people off, and they'll give undue authority to somebody that uses big words. But I think Zoner probably was inspired by W.C. Fields. W.C. Fields said, if you can't dazzle them with brilliance, baffle them with bullshit. So what Zoner did was he said, here's this dihydrogen monoxide. It's causing corrosion in all the metals of our society. So even if you get too much of it, you suffocate, meaning drowning. So he doesn't talk about the good things like you need it for trees to grow and fish to swim and our blood to flow. But you demonize it, which is what they're doing with CO2. And then he goes on to say, and now the scientists are finding it in fruits and vegetables, and they're finding it in mother's milk. And so all these kids start signing this petition to ban water just by the way he spun it. Now, I talk to a lot of people, and I say I can just use different words. I had one student where he knew the word bacteria, and I used the word bacterium and threw him. They say, I don't know what that word means. So a lot of the people are scientifically ignorant. They don't have the background in the language. And if you think about it, only 25% of the public hold bachelor's degrees. And that doesn't mean you have a degree in science. Like John Kerry, he has political science, but has no idea what climate is, but he became the climate envoy for the United States. Much less than 1% of the public has a climate science degree. So they can easily be baffled by someone saying, oh, I have a degree and you don't. Less than 1% have a chemistry degree, which is important for understanding. Less than 1% have a meteorology degree. And about 3%, if you want to understand the physics, like Will Happer does, they have about a 0.3%. So people don't have the background to challenge basically the bullshit that's pushing everything. Now, I have an ecology degree, and there's much less than 1% of the people have that kind of degree. But as an ecologist, I like to think we're a step above anybody with a climate science degree, because we have to look at all the factors. You got someone like Michael Mann really just looking at CO2. I had to learn about all the things that are affecting the ecosystems in California's Sierra Nevada. So you really learn about El Niños and La Niñas and the different kinds of oscillations that affect the ecosystem. If you don't, you're not a good ecologist. So, and you have to keep many possible theories in your mind instead of just saying, oh, it's all due to CO2. And in regards to, Einstein warned people, said, if you have unthinking respect for authority, just because someone says, I have this degree, then you're the greatest enemy of truth. So what you really need is what science needs is to have good debates. Okay, so what I want to start with is this push that CO2 is causing a climate crisis and extreme weather. And I want to show that it's a zonerism. And the first thing they did is the people that are pushing this have changed natural variability, and now they're calling it hydroclimate whiplash, which sounds intimidating. And the scientific fact, or call it a factoid, is that as the temperature warms, the atmosphere can hold more moisture. And this is what's causing all this extreme climate crisis they talked to. And Swain just pushed something in a recent paper he published. And to reach people with less than a ninth grade understanding, he used the idea of a little sponge can only absorb so much water. But if you warm the atmosphere, it becomes a big sponge and can absorb a lot of water. So the idea is what it is saying is if I squeeze out the big sponge, it's going to cause this extreme flooding. It's going to cause extreme precipitation compared to a little sponge. But the problem with that whole analogy is if they both only absorb a little bit of water, you can squeeze them out and only a little bit of water is going to come out. So it really avoids the whole dynamics of how moisture is really transported around. But using that idea, you'll say that you can now have floods caused by CO2 because it's a big sponge, or because the sponge can absorb more moisture, causes more evaporation in drier habitats. So you get all these journalists who don't know science, but they go to some alarmist who says, well, and will you see them repeat, oh, because it's warming, the atmosphere now holds 7% more water, so now we have more floods. And because it can hold more water, it causes more evaporation, so you have more droughts. And because you have more droughts, you have drier fuels, so now you have more fires. And what disgusted me the most is blaming the Los Angeles fires on climate change and this hydroclimate whiplash. And you had Michael Mann and Swain out here doing that. What they don't talk about, Zoner didn't talk about how good water was for fish and plants to grow. They don't talk much about the amount of moisture that a small sponge or a large sponge can absorb is due to the way moisture is transported around the world by natural oscillations. And then that amount of moisture transport, we'll call it absolute humidity, how much humidity is there. Most of the moisture gets absorbed from the ocean, but most of it falls back to the ocean. And then about 10% is transported to land. And on the side, in this case, on the west side of the Sierra Nevada, you get a lot of rain. On the west side, on the east side, you get deserts like in Nevada. So to deal with that problem, they'll just say, well, climate change causes the wet places to get wetter and the dry places to get drier. But even that meme is falling apart, which is why they've gone to this hydroclimate whiplash. If you look at satellite data of changes in precipitation from the last 20 years, from this study here, you would expect if it's climate change that maybe over 50% at least of the world would be experiencing some kind of significant change. But it's not true. 88% of the earth has no significant change. And only 6% has drier conditions. And those are represented here in the orange. And it's kind of scattered, and it shows like it's more local circulation effects is causing the difference. And that's balanced by the green areas, which has an increase in wetter precipitation. And the drier areas aren't because of more evaporation due to global warming. They're just because less moisture is precipitating out over those areas. And most of the land where floods and droughts could be causing harm to ecosystems and humans, you see there's very little change in those places. Probably the one place is the biggest change in precipitation was around the Pakistan area, which is, you see here in this green area. But this is probably one of the most climate variable regions naturally. But what you see, Pakistan had some floods in 2010, 2022. And so you got bombarded. The public was saying Pakistan emits less than 1% of the world's planets, but now it's drowning. So all the industrialized countries should pay for their climate crisis. And then to add to the heartstrings of people that say, and Pakistan highlights climate racism. Like for some reason, the floods are happening here due to racism, which blows me away that they would entertain that in any kind of scientific way other than try to manipulate your feelings on it. Well, if you look at the changes in moisture in Pakistan, which a scientist did, and after the 2010 floods, he asked the question, how much is it natural variability or climate change? And here's the changes in precipitation since 1920. And you see there's really no trend of more or less, but you do see major spikes of above normal precipitation and below normal. And probably the most deadly thing for Pakistan was the 1876, and I take it back, this is since 1850. 1876, you see there was a tremendous lack of moisture in Pakistan. And that created tremendous hardships. And it was known as the global droughts. You had the Great Famine of 1876. And in that area, it was like over 7 million. And worldwide, there were droughts around the world that they estimate over 12 million people died from this. And they attribute it all to El Nino. And it's not global warming. 1876, you can't blame CO2. You can't blame global warming. It was actually colder. And probably being colder is part of the reason it was so bad. The reason El Nino had a big effect is normally you have La Nina-like conditions. And a La Nina event is just a little more extreme, but you have a strong trade wind blowing all the warm water across the Pacific and has it build up in the Western Pacific warm pool in the Indian Ocean. And there you have all this convection that supplies all this moisture for the monsoons. But when you have an El Nino, the winds shift, the area of convection shifts towards the Americas, and that's when we in California get our rain. We get more droughts during La Nina. When that happened in 1998, we got flooded in California, and Indonesia had tremendous droughts. And it's the same thing for all the monsoons. When the El Nino goes, you're getting less water being supplied to these monsoons. The other thing is the Pakistan Indian area is really affected by the changes in what we call the Hadley circulation, which is a north-south circulation, where you have the equator where the sun's rays are the strongest. And so that draws in the air from the north and the south. That air is picking up moisture along the way. And when those trade winds from the north and south converge, they have no place to go but up. And so you have this tremendous convection upwards. As it rises, it cools. And so you have all this rain in the intertropical convergence zone. And probably 30% of the world's rainfall happens right here in the intertropical convergence zone. And it's responsible for the wet and dry seasons of the tropics. Now, the air, once it's up there, it's all rained out. Now it's dry. And what goes up has to come down. So the air eventually has to come down. And it comes down about 20, 30 degrees north and south, and it's dry. And where it comes down, it creates dryness. And it creates a high pressure system because of the sinking air. And that high pressure system blocks out the moisture from coming. It's usually clear, sunny skies, which can heat up the land a little quicker. And it's usually these kind of high pressure systems that cause our heat waves. Now, what the this is sort of it's not always at the equator. When the sun moves northward, due to the way the tilt in the axis happens on the Earth, the ITCZ, the intertropical zone, moves northward. And everything, say, in this red zone would get this rainy season. Everything below that would have a dry season. And then in the winter, because the sun will now do the tilt of the axis move southward, the rainy season moves south, and the red areas get very dry seasons. So you have this natural seasonal whiplash, this hydroclimate variability, just because of the way the sun and the orbits change where the intertropical convergence zone will happen. And along with those wet seasons, the high pressure zones move back and forth. So you look here where you have these Pakistani floods, they're associated with when the ITC is farthest north over India in the Pakistan area, and they depend on it. And they control the monsoons along with the El Nino, La Nina conditions. So if we look at what happens normally in India, we can see here that when you have the monsoons, in the summer monsoons, the way the air currents, they carry all this moisture up into India. It doesn't get past the Himalayas, so you can see the orange and yellow areas on the other side of the Himalayas is drought. The winds carry so much moisture, the town of Masanram is known as the wettest city on the earth because all that moisture gets transported there. And here it's listed at 11,800 millimeters. Well, you go just east where the winds have a slightly different effect to Bikaner, and Pakistan is in that kind of yellow area surrounded by the red. It hardly gets any. And in fact, Pakistan is mostly, has a large segment of the country is desert because it just doesn't get that much rain. But it's still, just to survive, it needs the monsoons. Well, if the monsoons reach Pakistan or not, the monsoon moisture is going to control when it has floods and droughts. And the flood of 2022, you can see what happened is in the far eastern India had much less moisture than normal because the winds didn't deliver the moisture. The western part of India and Pakistan got more moisture. So you see in western India, you have all these blue areas where you had an excess of moisture. And when you have a desert, you don't need much more excess to cause these kind of floods. So it wasn't that warming, that there was a bigger or smaller sponge squeezing out the air. It was squeezing out the same amount of moisture, but it was just a matter of shifting it from the eastern India to the western India. But nonetheless, you have these gullible politicians, and they believe if they all start driving EVs, they will stop this natural variability of the ITCC and the El Nino La Nina conditions. But it will do absolutely nothing. But they are able to push this kind of agenda, and people go, "Oh, that sounds good, so let's do it." And I'm not against EVs if you want to buy them. I'm just against thinking that they're going to control the climate. It's a hoax. And just to add to the power of this shifting of this intertropical convergence zone, we know the way the orbital axis has changed, that the international intertropical convergence zone has been shifting. And back in 7,000 years ago, it was farthest to the north. And the further north it is the stronger the monsoons are. And it has been shifting further and further south due to the change in the axis tilt, and that causes weaker monsoons. What we know for historical, you look at this climate change issue, is the Sahara, when it was far north 8,000 years ago, was a lush savanna with lots of wildlife, with lakes and hunter-gatherer tribes living off all of this wildlife. As that ITC moves south, the rains move south, and the high pressure system set up over the Sahara, so no rain gets delivered to the Sahara. So you get, it changes into a desert because of the way moisture is transported, not due to CO2, not due to climate change and human cause. But you also have, you see this sort of a belt of the same latitude. We have all these deserts, both north and south of the equator. And the other thing is, they try to say, well, high temperatures cause more evaporation, but the opposite is also true. When you have dry land with no clouds, you get higher temperatures. The ground heats up far more dry land than it does wet land. So you see some of the greatest temperature increase, or record highs. Death Valley in California is 134 in 1913. Can't blame that on CO2. Sahara had even higher, but they challenged that record. But it was 136 in 1922. And now with satellites over the Lut Desert in Iran, satellites estimated the ground was 177 degrees because it wasn't. So it's all this high temperature, again, doesn't have anything to do with CO2. The deserts don't have anything to do with increased evaporation. They have to do with the increase, the change in the way moisture is delivered to those areas. Now, on the opposite, here in California, where Death Valley is, where I work in the Sierra, I could look and see the desert on one side of the crest and moist habitat on the other. But we have these coming megafloods, and it's due to atmospheric rivers that people are the satellite data has allowed us to detect these atmospheric rivers better than climate balloons are ever able to do. So we've noticed since 1990. Well, the last big flood in California was long before global warming, long before rise in CO2. It was the Great Flood of 1862. The Great Flood, it was so bad that Sacramento had to move the center of government, state government's capital was Sacramento. They had to move it to San Francisco until the area dried out. The Sacramento Valley was known as a marshland back in those days. These atmospheric rivers had the worst floods, despite a small sponge due to global climate change, during the Little Ice Age and during the cold winter. The atmospheric river, like we've just experienced here for the last 4 days, happened in December and January that caused the floods. And they can tell by sediments in lakes in the bay that every 100 to 200 years, you get these mega floods. It's due to these natural oscillations that they can't quite pinpoint. But you see that in the 1300s, 1400s, 1600s, 1700s, 1800s, we've had these mega floods. And it's mostly because atmospheric rivers have got focused on California. So the extreme flooding is not correlated at all with CO2 or at all with global warming. Now, I'm imagining most people aren't aware of an atmospheric river or how it happens. If you go to the National Weather Service has a website, earth.nullschool, is down at the bottom if you want to copy that. But you see the light blue ribbon across just north of the equator or on the equator. That's the the intertropical convergence zone. And if you want to see how much moisture is there, on January 31st this year, I went and I downloaded this and then tagged how much moisture was represented. They measure the total amount of water that can precipitate in a column of air, a meter squared by a meter squared, was like 65 grams over here. A little further, only 55. You go to the desert, there's only like 4.7. So you can see there's a much greater difference of how much moisture is brought to where. For the atmospheric river, it sort of emanates out of the ITCZ here, goes across Hawaii. It's why often San Francisco calls it the Pineapple Express. It has about 51 kilograms of water. When it gets just to the coast of around San Francisco, it's down to about 33. The more floods we get, it's the more persistent. This last atmospheric river lasted for like 4 days. It just left. We had some off and on rain all the time for the last 4 or 5 days. So people say, oh, it's due to temperature. Well, it's how long these transport events are focused on a certain areas while you get a flood. And so you have to look at all these high pressure and low pressure systems and see what traps these. If you go to the east side of the Sierra Nevada, the desert's only got 2.4. So again, the transport's causing a little more of dryness there.
Quick question. Do you know off the top of your head, if you had 65 kilograms of water in 1 square meter and it all fell to the earth, how much would that be, I wonder? I'm curious.
I don't know that offhand. Most of the time you say in these areas, most of that water, there's still some always going to be in the atmosphere, but most of that water will fall. In these atmospheric rivers, instead of rising to the top and just falling right back down, it emanates out in a more shallow convection current. And that's where a lot of these atmospheric rivers are only about 10,000 feet high in altitude, where the convection and the ITC will go up to maybe 30,000 feet. So exactly how to give you that number, I can't say, except for looking how it's affecting us here.
I was reading up on that flood of 1862, and they were saying that over a period of 43 days, 10 feet of water fell on each on each unit of area there in the form of either water or snow. It killed 1/4 of the cattle, and it created a lake that was 6,000 square miles. Pretty amazing.
Absolutely. Tulare Lake down south, you could see it. You had boats and canoes on it. It partly why it's hard to answer the question, how, does all that 65 kilograms fall, is because the trade winds are constantly transporting moisture to the ITCZ, it sort of keeps supplying some of the moisture to that atmospheric river. So, I don't know how to distinguish between those changes in transport and whatever, but it was a tremendous amount of water. And again, it has nothing to do with temperature, nothing to do with climate change and CO2. You have to understand these dynamics, but no one wants to educate the public. I'm trying to educate the public. You're trying to educate the public. And we have all these alarmists trying to baffle them with bullshit. So just give you an example of, you have this, at the same time, you have this atmospheric river running through the Atlantic. And the way the pressure systems guide it, the Sahara still only gets about 4.7, where Iceland was getting about 22. And then most of the water rains out. So by the time we reach Greenland, you're down to 1.2. So it's raining out at different places. But again, the main idea here is it's the transport of moisture is causing these different changes. And these atmospheric rivers change where they're going to be making landfall. So you're going to have this atmospheric river whiplash naturally, as we've had all the time, because the pressure systems are always guiding it one way or the other. Now, we know there's a third oscillation involved here. So I had the El Nino oscillation, you have the ITCZ, and another major one is this Madden-Julian oscillation. And again, I said this rising air creates heavy rainfall, sinking air creates dry, high pressure systems, sunny areas. Well, this Madden-Julian oscillation starts in the Indian Ocean, lots of rain, and the air comes down, but it comes down and creates a high pressure system a little bit closer. And this moves. Well, how it's different is the El Nino happens like every 3 to 7 years. This Madden-Julian oscillation happens every 30 to 60 days. And so they map it. And you can see that when it starts off, when they'll call it phase 1 in the week 1, the Indian Ocean is getting lots of moisture, and Northern Australia is dry. And then by the second and third week, it moves eastward, and now the Indian Ocean isn't getting it, but now Australia is getting lots of water. And then a couple of weeks later, it's further eastward, and now Australia is dry again, and most of the moisture is falling in the Pacific, and then the oscillation dries out because you have this cooler waters being upwelled from the eastern Pacific. So you have this whiplash of dry, wet, just naturally from this Madden-Julian oscillation. And it also has an effect on the jet stream, which guides all these weather events. And it changes the temperature gradient in the ocean, where you have converging air and descending air. It makes the jet stream undulate a little more. And when the jet stream has a ridge, it tends to cause the air to converge and sink. So below a ridge of the jet stream, you get dry weather, you get a high pressure. And then when it forms a trough, the air starts to diverge, and that causes the air to rise. It creates a low pressure. And so there you get wet temperatures. So just as a jet stream moves from the west to the east and undulates, you're having this whiplash of dry weather and wet weather. And here's the thing, they've looked at one case where the Madden-Julian oscillation in India caused these undulations in the jet stream, which end up causing a heat wave in South America. And because what you're having is these rising and sinking air is moving, and it's just causing these high pressure, low pressure systems. So you can't blame the heat wave in South America on climate change. It's sort of part of these natural variabilities that is causing all these changes between wet and dry areas. But it doesn't take long for the alarmists to jump on it. And one of the big push for this climate whiplash is Daniel Swain. He was a student of Noah Diefenbach, and they're both good buddies with Michael Mann. Can you believe that? But just to repeat what Thomas Sowell was one of my favorite authors. He said, con men have learned a long time ago their job is not to convince skeptics, but to enable the gullible people to continue to believe what they want to believe. And so you can make up these stories. Once they've convinced you that CO2 is causing a climate crisis, you can make up almost anything and people, oh, damn, that's true. And I've had people call my house and say, I'm causing humans to go extinct. because I question this, which is what scientists are supposed to do. But they call you a denier for engaging in good science, which tells you how much these gullible people are being. So the worst, again, is what really triggered me to want to talk about this, is blaming the Los Angeles fires on hydroclimate whiplash. Michael Mann was quick to be interviewed on CNN and say, "Oh, global warming made everything drier, and that's why you had the fires." Daniel Swain doing the same thing. So I want to talk a little bit about the fires. And I've talked to a number of people, and I've been blogging about fires. Is part of, as an ecologist, I had to understand how it affects the whole ecosystems. But if you look at the EPA, you'd like to think you can trust the EPA. Hopefully, we have some more honest people coming into play now. But if you look at heat waves, it's in this cause. If you looked at heat waves for the last 120 years, you see that there's no trend due to global warming. There's no trend due to rising CO. And the worst were in the 1930s. But if you want to push a narrative to enable the gullible people to still believe, you cherry pick the data. And when there was the fewest heat waves in the 60s or 70s, that's when you start your data. So then the EPA, even though they have this, they push this. And they start in the 1960s. And look, rising CO2 and rising heat waves, they're all connected, so it must be true. And people just go, "Oh, okay." They don't dig any further because they don't have the science background to do it. Well, the same thing happens with wildfires. And the EPA's climate change indicators talk about wildfires. Well, if you put it in the background of historic wildfires, Swetnam in 1996 published this, and he went around throughout the Southwest of the United States, and he looked for charcoal and burn scars and burnt debris and whatever. And this graph shows the amount of sites that had any kind of evidence showing there had been a fire there. So the more sites, you have the peaks there. And that's really a proxy for how much burned area we had in the past. The more sites, the more burned area. It's not quite quantitative in the actual area, but it's really a very legitimate. And you see that once fire suppression happened after the 1900s, because people wanted to stop fires because it could destroy timber and destroy colonies and whatever, you see this dramatic drop off in the 1900s because the Forest Service developed this 10 a.m. rule. If they spotted a fire, they were going to maneuver all the energy they could to put the fire out by 10 a.m. So you had this tremendous fire suppression happen. And so you see by the late 1980s, 1990s, there was hardly any fires relative to the 1700s when it was colder. So is it colder? Well, what the Forest Service, what the EPA did is, instead, they show you this graph. Say, look, since 1980, look at how wildfires have increased. That correlates with CO2 and global warming, and therefore CO2 is causing more wildfires, which is, again, it's a zonerism. You're not telling people the whole story. So if you look at the United States and where the most fires happen, it's an amazing difference between and these fires are controlled by relative humidity, and that controls how the fuel moisture and the flammability. Well, if you look at the Western United States around Southern California, the average relative humidity is 20 to 40%. And the alarmists like to use vapor pressure deficit, which is really the same thing. But when you have 100% relativity, we know that as the dew point. That's the air is cold enough it can't hold any more water. But when you're at 20 or 40%, the air is holding only a third of the amount of water that it could hold. So it doesn't matter if it's a big sponge or a small sponge, it's only holding a little bit of moisture. Where you go to the eastern United States, you're getting 50 to 70% relative humidity. I grew up in Boston. You had a lot of rainfall in the summer. When I went to California, we don't have rainfall here at all in the summer. It's just a natural drought, and I'll explain why. But it's the people in the East don't understand how dry California gets. And that's why it's been the focus. It's cherry picking this one location as the place for the most wildfires. And the reason the East Coast has such high relative humidity is because of moisture transport from the Gulf of Mexico or Gulf of America. I'm not sure what we can call it right now. But you see this, if you travel across Texas, West Texas would be brown. You get past Abilene, all of a sudden it turns green. Is that big of a difference? It's startling how quickly it turns green just because of the way the moisture gets transported. Well, to explain what relative humidity is, it's really a relationship of absolute humidity, which means how many kilograms of water is in the air, relative to the maximum capacity of the air based on temperature. But only the coldest regions, and you see them here in the really light turquoise, have 100% relative humidity. The places in the Western United States have some of the lowest, 20, 30, 40%. The deserts have some of the lowest because they just don't have that much absolute humidity, that much moisture being transported to them. So how much is California going because climate change is affecting the amount of moisture? Well, if you look at studies that have looked at the Sierra Nevada, where most of the moisture hits and then rains out, you see there's lots of volatility, lots of variability, but there's no trend. You have years where it's more than usual and less than usual. Well, what happened, the reason California is so dry is we're a Mediterranean climate. And Mediterranean climates have a drought in the summer, and then they have a mild, wet winter. And it's really a seasonal whiplash between dry and wet. And it happens to do, again, with the ITCZ and where its high pressure systems in dry areas happen. So if we just look at the Northern Hemisphere, the trade winds go from the east to the west, and then you go outside the tropics. Now you have the westerly winds going from the west to the east. And normally they would carry all this moisture to the west coast of the Americas, to the Mediterranean area. And it's the same kind of dynamic down in Australia and South America. But because the ITC shifts northward during the summer, it kind of puts this high pressure system in place that blocks that flow of moisture. And so the moisture that hits that high pressure system is directed upwards. So you have these boreal rainforest up in northern Washington to Alaska, because that's where the moisture goes in the summer. But then when the ITC moves southward with the winter and the change in the tilt of the axis, that high pressure system moves southward. And that allows this moisture to give these areas with the Mediterranean climate their winter precipitation. So you have a summer drought, winter precipitation, totally natural. Where this happened probably shifted as the ITCC has moved southward over the years, making the Sahara a desert. But this is why we have it. And what makes it even worse is the El Niños also affect us in that way. So those blocking high pressure systems get worse during a La Nina winter and less during an El Nino winter. So we have this kind of variability going on. And people say, oh, the Los Angeles was due to this unusual drought. Well, no, it wasn't. It was a La Nina winter right now. And so you have a delay in how much moisture reaches the Los Angeles area. Well, if you're in a Mediterranean climate, you don't have enough moisture to really grow a lot during the warm season. So you get this kind of vegetation that doesn't require a lot of moisture and a lot of growth. And so it's mostly these grasses and the shrubs and the chaparral. And the chaparral shrubs are all geared to fire. They have their seeds only germinate after a fire. They have buds that they keep kind of hidden until a fire comes by, and then they sprout. And some of them even amplify fire by having more volatiles in their leaves. So the importance of vegetation for wildfire ignitions is not going to be due to global warming. It's going to be due to what kind of vegetation you have. A simple spark can ignite a grassland fire. In 2017, the biggest fire, it's now the third biggest fire in California, was called the Mendocino Complex Fire. There was a rancher driving a metal stake into the ground out in his fields. It hit a rock, it sparked the grass, and that grass fire took off and created the biggest fire in California at the time. So it had all to do with the vegetation in a natural spark. It didn't have anything else to do with anything else. Well, you compare that to a tree. Now, a tree can get hit by lightning, and I've walked around the Sierra Nevada, and you see a lot of different lightning scars. The lightning strike will have temperatures of 50,000 degrees Fahrenheit. It's like 5 times hotter than the surface of the sun. Yet it doesn't ignite the tree. It might vaporize some of the moisture in the tree and cause a scar like this, or I've seen one where it blew the top off of the tree. When a lightning strike usually causes a fire, is because there's a lot of grass or duff that is easily ignited at the bottom of the tree. To burn a tree like this, you need more kindling. If you had a campfire, you know you need little small twigs and sticks to build up enough heat for a sustained amount of time that then can ignite a bigger tree like this. Well, so one of the problems with wildfires is that fire suppression allowed kindling to build up beneath the trees. And so it's this kindling that's actually spreading the fire. It's easily ignited, it brings it in. But if you have enough of it, enough of these shrubs, then you can ignite the tree. So unless you account for the amount of undergrowth, you can't blame it on climate change. And it's this fire suppression that causes undergrowth to allow the trees to burn more. But even given that, the trees have not, woodland fires have not really increased in California. Now, if you're a fire manager, you're a land manager trying to look at how fires happen, what you do is you look at what kind of vegetation you have. And you have grasses or 1-hour fuels. What that means is it could stop raining in the morning, and by afternoon in the hot sun, it's highly flammable. It doesn't take climate change. It just takes a few hours of dryness to dry it out, because it's such a small diameter type of fuel. It reacts to any change in the moisture in the air. 10-hour fuels are like the dry twigs of shrubs. And so any of these twigs that are have a diameter of size of a quarter or less, they're easily ignited within a day or two. It's climate change and temperature is totally immaterial. Bigger trees are going to need a longer time to dry out. But these are dead fuels that we're talking about. On top of that, the Los Angeles fires, everyone knew they were coming because of the vegetation, and they also knew that the Santa Ana winds can wreak havoc. Now, but 75% of the Santa Ana winds don't cause a fire. It requires an ignition to happen simultaneously. But Santa Ana winds happen in the fall and the winter because the desert can cool much quicker than the Pacific Ocean. And so that sends up a temperature gradient, a pressure gradient that drives air from the high deserts down to the ocean. And when you have pressure systems set up, it will amplify that. And then as those winds go through the canyons down there, it amplifies the winds even more. Like as a kid, we used to put our thumb over the end of a garden hose and have it squirt a lot faster. It's the same kind of theory. So these Santa Ana winds happen because it's colder in the winter, and because the absolute humidity in the desert where they start off is so dry that the relative humidity, as it was hitting the Los Angeles area, was down to 10%. Now, if you're a rancher that wants to know how to bale your hay, or you're a fire expert and you want to know when it's safe to have a prescribed burn, you have to look at the moisture content of the hay or the grasses and the shrubs around you. And so there's been tons of studies. And you look at here, the blue kind of shows the relative humidity. The left is showing you temperature. Well, when you have below 10%, like the Santa Ana winds were delivering, the fuel moisture of those 1-hour and 10-hour fuels was down to 2%, highly flammable. And it didn't matter if the temperatures were below freezing or the temperatures were above 109 degrees. It was all 2% because it's relative humidity that's driving this fuel moisture. If you get up to 60%, now you get over that kind of safety zone of 9 or 8% like you have in the East Coast. But to push saying these fuels are dry because of warmer temperature is baffling people with bullshit. It makes sense because you think warming air dries things quicker. But if you really look at the kind of vegetation in their response And you could probably do a study at home, take a piece of paper, soak it, hang it up, and see how quickly it dries in your house. That's what happens with these grasses. The other thing with this is the amount of grasses that ignite easy and spread fire so quickly is increasing because of the landscape changes we've done. Malibu Canyon was right near where we're seeing some of these Los Angeles fires. It was getting 2 fires every 10 years. And so what you had is a chaparral shrubland turned into a grassland. And a lot of it was invasive grasses that now took over after the disturbance. So you're making it more easy for these fires to ignite and allowing them to spread much quicker because the grasses just burn quicker. I stood above an area that had a cheatgrass fire. You couldn't outrun it. There's no way you could outrun it. The fire would move so fast you'd be caught within 10 yards. Similar places around there. 1970, that area in the background was mostly chaparral shrub. It had a fire and it kind of reduced a lot of that shrubland, added some grasslands. And the third fire in 2003 turned it into almost all these 1-hour fuels. So what the humans are doing, and they're also allowing this cheatgrass to come in. It's from Eurasia. It germinates in the winter because that's when we get our wet season. It's dried by April or May. So now you have this highly flammable grasses that's lasting from the early summer throughout the fall. And so we're just increasing the ability to have these bigger areas that fires, carry them into woodlands. And so it's the Forest Service. But if you look at studies, CAL FIRE looked at this, the suppression caused a drop in all fires, but still throughout this, grassland fires caused the greatest extent of burned area. It's not a function of climate change or temperature. And you look at the woodland fires are still much less than they were in the 1920s. It's the grassland fires that are carrying most of the load. So Michael Mann got up and said, what's most disturbing is now we have fire season all year round during the cold winter, and that's due to global warming or climate change. He didn't say global warming. He said, well, that doesn't make any sense. How does the winter cause more fires? Well, what it is, if you look at this data is from a study by Balch in 2022, I believe. But you see the blue is lightning fires. That's our natural fires. And that peak is June through August. And then you hardly have any lightning. You hardly have any lightning at all in the Los Angeles area during the winter. But you have lots of humid ignitions. And you have humid ignitions because of accidents. They had an increase in homeless people trying to keep warm in their tents, catching the tents on fire. They've had more arsons. You got more people. You have an electrical grid. So when you have these big fires, big Santa Ana winds, you blow down some of the electrical grids. So what you're having is the reason the fire season is going all year round is not due to climate change, but due to more people and more people doing careless things. But still, we've had these scientists, supposedly climate scientists, they're sort of cherry picking and tuning their models to, I spelled that wrong, maximize this danger. But they claim we demonstrate human caused changes caused half of the increase in dry fuels since the 1970s. Now, if you read this study closely, they'll say they use metric to say how much aridity was in the fuels. And they say, well, if they use one based on temperature, and the temperature was derived from 16 climate models or whatever, you had extreme fuel aridity. But if they use the ones based on precipitation, it was a little more subdued or didn't give them much of an answer. So they didn't use those ones to make their claims. They also say, well, they admit that natural climate change had something to do with it because they say even if we remove the anthropogenic, the ACC climate signal, you still have an increase in fires due to natural variability, which would be the La Niñas that we've had. But they show there's no significant trends when they look for the changes in monthly fuel aridity from 1948 to 1978. Well, CO2 was still growing then, but that didn't cause any change then. Only now did it cause it. And so what they did, like they always do, is they cherry pick the data. So they give you this correlation showing that aridity has increased since 1984. And this fire has burnt area has increased since 1984, and they don't really account for. They mention it, but they don't account for the buildup of shrubs and grasses from fire suppression and disturbance. So, if that's not good enough, now you had someone from UC Riverside blame the fires on CO2 because it's helping plants grow, which is just, it's like, I don't know, they're just addicted to finding some way to blame CO2 for everything. If it's hot, it's cold, it's more fire, less fire, you have more growth. Oh, that's bad because you have more fires. And, I start off with W.C. Fields' baffle him with bullshit. He says something that's kind of true for the way our climate scientists are working is you can fool some of the people some of the time, and that's enough to make a decent living. And I give you a lot of credit. You've been on Twitter and everything, trying to teach people, and that's all we can do. That's what the CO2 Coalition is trying to do. Say, here's another side of this. Think about it. And the United Nations, instead of bringing in skeptical science to have a debate, they bring in Greta Thunberg, which,
Right.
who knows jack shit, or you give John Kerry, who's a political scientist, the climate envoy. It's amazing of how much bullshit is going on.
100%.
People don't pick up on it.
Yep.
Well, the reason I want to talk about last year, I've given a couple talks to San Francisco's Economic Roundtable Forum. And I gave a talk about some of these natural variabilities that could explain what people are blaming on CO2. And I had this one guy, he's a PhD, medical doctor, who disagreed. And what he did, he held up this picture and said, "You're lying. This is what climate change is all about." And I said, "Really?" He said, "Nope, that's all you need to know." And, I saw that picture a long time ago, and what amazed me, it's got more views than anybody, any other picture. And you can see his left front foot is got a club foot. So he's already genetically mutated in some ways. But you blame this on climate scientists. And the National Geographic photographer went out trying to find some kind of a photo moment that would make you feel sorry for climate change. And so that's what they did with the polar bears. And I couldn't argue with this guy. It was like, Mark Twain said, it's easy to fool people, but harder to convince them they're fooled. And that certainly was the case with this. And so I did a couple of months later, they had someone from Polar Bear International speaking about how climate change was killing polar bears. And if you go to their website, they'll tell you some weak stuff, but what you'll see in the corners, they're always asking for more money. They're always trying to make more money. And so, "Oh, Paul just gave 100. Oh, Joanne just gave 1,000. And every 15 seconds you get bombarded with that. They're really they're just grifters. But anyways, his argument was that climate change is threatening polar bears because the polar bears catch ring seals on ice. That's a true fact. And if there's no sea ice, there's no access to the seals. And that's correct. That's, you're not going to catch them unless it's by sheer luck that way. But what I call the polar bear zonerism here is what the guy from the Polar Bear International said, well, less time on the ice means fewer captures, more starvation, decreased reproduction rate, and a population decline. And now because sea ice is melting a little earlier and forming a little later, the polar bears have less time to hunt on the ice. And that's going to cause all these problems. Well, what they don't tell you is time in the ice is a totally irrelevant statistic, in which I'll try to show you why that's the case. The ring seal is their main food supply. And the ring seals stay in the Arctic all winter. Temperatures are down minus 36 or whatever. The only way is the seal can survive, it has to have breathing holes in the ice. And the only way a ring seal can make breathing holes in the ice, it has to be brand new ice where it's thin, where they can butt through the ice with their head. And then as it gets thicker and thicker with the cold winter, they can gnaw and claw and keep it open for themselves. But if you have multi-year ice that's been maintained, they can't, is 3 meters, 4 meters thick ice, they can't make a breathing hole in enough time before they suffocate. So where you find them all in places where the sea ice melts every year. And when you actually have more melting ice, you have more conditions that allow more seals to make breathing holes and survive and supply the amount of food that polar bears need. Here's a little, some data from the LAPTEP-C, and I didn't put down who I had it from, but it's I can get it for you. You're showing that indeed the ice is melting a little earlier and forming a little later. Well, at this point is when most of the seals now go out to the open ocean. They've been kind of tied to their breathing holes for a long time, and they want to go find where the ice is melting, causing more photosynthesis, blooms of plankton and zooplankton and more fish. But they're not accessible to the polar bears. Then when the ice forms, and so you're going from October to early March, the ice is formed, plenty of time for the bears to hunt, but the seals still spend 90% of their time in the water, not on the land. The water is only at the freezing level. The land is at minus 36. So where do you want to spend your time? And they'll make multiple breathing holes. So if they feel a bear is at their breathing hole, they come up, they can sense it and pop up at another one. All the bears lose weight during the winter when there's tons of ice. The amount of ice there's plenty of time for them to hunt, but they don't still have access. It's almost equivalent to the time that I showed in yellow, that when it's open seas, that the access to the seals is about hardly anything. The seals are going to spend 90% of their time in the water. The only time that the ice is really an issue is when the seals have to give birth to their pups, and each year they have to molt their skin to grow a new layer of blubber. And so that starts in late March and lasts through June. And then when the sea ice melts, the seals are happily off looking for fish in other places. Females, pregnant polar bears, they don't hunt on the ice during the winter. They know it's worthless. They go in their dens around October, and they emerge around March at the same time the ring seals are giving birth on the ice. And because the pups are more vulnerable then, and because when you're molting, it's easier for the polar bears to sneak up on you and eat you. That's the time the polar bears can double their weight, triple their weight. They've even had some that I think they've had quadruple their weight. And that gives them enough energy and fat to last through the famine that happens during open water season and thick winter season. So the real key is how these ring seals are doing. So less ice, a melt season helps them. They don't see them that much, so they don't have a good figure, but there's in millions. No one argues at all that they're threatened in any kind of way. They're considered an animal of least concern. The more seals, the more bears, the more fatter bears, the happier bears. So, and the other thing is they don't tell you is melting ice not only helps ring seals make breathing holes, but it also increases the abundance of food supply for the seals and thus for the bears. So we have all these studies that have shown that there's these changes in phytoplankton concentration. They're increasing 50, 60, 70% because you have less ice. So you tell people that, it's, oh no, it's killing the bears, but I don't know what to tell you. And the other thing, you start looking at, okay, where is all this ice melting? Well, here's a picture from NOAA, Arctic sea ice winter peak in 2023. So this is it was the fifth lowest on record. So where is it the lowest? Well, you look at what they compare it to is that kind of orange line shows you where the extent was back in the 1980s. And the melting is happening only in a few areas. If I look at, this is it's 60 degrees latitude, and the Arctic Circle would be about 67 degrees latitude. Most of all the area is frozen solid in March. There's a ton of ice there. Global warming has not stopped that. The places that lost ice are just north in the Barents Sea and north of Svalbard. And So why is it there? Why is global warming melting the ice there and not the sea ice any other place? Well, the reason is that is where warm Atlantic water flows into the Arctic. And the more that water transports heat in, the more it melts. So this area inside that circle that's melting is all melting due to this transport of hot water from the Gulf Stream, and it goes to the North Atlantic Drift and the Norwegian. And as that warm water comes in, then it circulates around the coast on the shelf, so that the seas around the edge are thinner, but they don't melt completely, but it allows them to melt every season. So the main cause of the melting we're seeing is not CO2, but it's changes in the transport of this warm water. Now, I had a bet with this physicist from UC Berkeley. I said, and I still hold to this, I think by 2030, we're going to start to see an increase in sea ice, because the way the meridional oscillation changes how much warm water flows into the Arctic is going to change, and we're going to see the sea ice start to grow. So we bet a couple bottles of wine. And he came back to me a year later and said, well, you never told me about all these warm waters flowing in. I said, well, I was on you. I knew that. That's part of what I was arguing. And but you're a PhD in physics of astronomy, but you don't really look into what's causing all this stuff. So he's a little nervous he's going to lose the bet. But anyways, you can see where as the water flows around the coast, it gets driven up onto those shallow seas, and that's where we're seeing the ice melt. And the other thing to consider is in the winter, and I did this again from the National Weather Service map. You can look, this was January 2024. If you look where the Atlantic inflows are happening, temperature's 2.5 degrees centigrade. If you look where the North Pole is, it's minus 32. And you go in the Gulf of Boothia, those islands in Canada, it's down to minus 29 because they're not being affected by this Atlantic inflow. And the other issue here is this warm Atlantic water is saltier than the water in the Arctic. So between about 100 and 900 meters, you have this reservoir of warm Atlantic water that can melt all the sea ice. It can melt it all 2 or 3 times over. It releases so much heat that it's way more than what CO2 could do, but they don't talk about it. So if you have the winds remove some of the ice or remove some of the fresh water that kind of insulates that warm Atlantic water, that water can rise to the surface and heat up the Arctic. So a large reason why we have this global warming issue is due to the Arctic, they call amplification, but it's actually the release of heat from the Arctic that's raising air temperatures. So, and to show you this, they had, after the Arctic oscillations, the winds changed and blew out a lot of ice and a lot of the thick ice. Well, people went up and measured how that changed. Well, the heat from this Atlantic water, without the ice, you had this open, what they call them open leads. It was releasing 700 watts per meter squared of energy. Over a month or so, it starts to thicken and now becomes 4.4 meters of thick ice. Well, now it's still radiating 80 watts per meter squared. When it gets to be 1 meter thick, as the winter goes on, it's still doing 30 watts per meter. And 3 meter ice is doing 2 watts per meter squared. So all this heat is emanating from this reservoir of warm Atlantic water, and you compare that to 100 years of CO2, it's only adding 2 watts per meter squared. So what is going to melt the ice? It's going to be the stored Atlantic water and how it interacts. It's not CO2, but that's what they're blaming on it. And you see them talk about Arctic amplification, but they blame it all on, it's open water due to CO2. It just doesn't make sense if you understand all the thermodynamics going on in the Arctic. So you got the average monthly Arctic sea ice is now since 1979 has been declining. So is that a correlation with CO2, or what we call the Atlantic meridional overturning circulation? With this AMO, we see what happens is the northern Atlantic goes through phases of 20, 30 years where it's warmer and then colder. It's the more transport of heat coming from the equator up into the northern Atlantic. So when they saw in the 60s through the 90s, it was a colder time. In the studies at that time, you had someone by Jonathan Call, Mark Ceresi, who's actually turned out to be a big climate change alarmist. But their study, they said that in the past 40 years, we see no evidence at all of global warming. And in fact, and they actually see some cooling trends, which is what you would expect with this AMO. It was not due to CO2. And the reason they didn't see it then was because of this AMO. And then when it shifts to the warm phase, we see more warm water coming into the Arctic, and we see a decline in the sea ice. And you see it since the 1990s. And you also see it back in the 30s. Now, we don't have the same kind of satellite data and other data that was used for these studies, but the Danish made some pretty good sketches of where sea ice was. So in 1937, they sketched in August the extent of sea ice, because this affects the way they can ship and trade and do everything else. Well, then it was like 310 parts per meter squared in CO2. Well, here's data from NOAA showing decades of change in sea ice. Well, in 2000, CO2 was up to 368 parts per meter, but if we compare that to the Danish sea ice, it was more than it was back in 1937. 2010, you see it's getting a little less, and you see it's a little more, but if you use the island of Novaya Zemlya, and I don't know if I'm pronouncing it right, but you use that as a reference point, you see that the amount of sea ice has been reduced around that island was about the same as 1937 as it is now. So there's not a trend due to rising CO2. It has to do with how much moisture, warm heat is delivered into the Arctic via the Gulf Stream. All right, I have to end that.
Okay, fantastic again. Are you a fan of Javier Vinos has the winter gatekeeper theory?
Yes, and I like a lot of what he says. I don't read him all the time. He had me review a book on oceanography for him. Me and Judith Curry did. But I think he's very bright. I know he's often on Judith Curry's site, which she's very proud of also.
And do you think then that we might see multi-decades of cooling in the Arctic then as the AMO switches?
I definitely think that's partly why I made my bet for wine.
Yeah.
It wasn't an expensive bet, but I think I'm going to be drinking.
See, I just want to bring a couple other things up here. Last time you said this interesting thing that there was a study in 2013 that found that 34% of long-term weather stations with over 70 years of data had cooling trends. Do you have any update on that? Or that blows my mind in general. We're supposed to think it's global warming. It's warming everywhere.
I don't have an update, but I do have that picture. You see this data point, and this is from the Wickham study, and it's using all the Berkeley Earth surface data. All the blue dots represent cooling trends, and the red dots, crosses, represent warming trends. And so what you see is most of the warming trends, the solid warming trends, are where you have urban heat islands. And where the cooling trends are, and it's actually where the jet stream dips down and allows cold air to come down into that area, which is what we're seeing this winter. And, you're getting snow in Jacksonville, Florida, and down in New Orleans and such. That this is 70 years of data, 70 plus years of data that is showing trends. It was more interesting to me is you find warming trends right next to cooling trends. And for me, that's exemplifies how much these temperature trends are due to landscape changes. You can't blame, a general oscillation, or you can't blame CO2. on having one weather station warming and another station cooling. And the big thing is going to be urbanization. And also if you have lack of vegetation or you dry a wetland, all those things can cause a different shift in how things are warming or heating. That's the reference you were referring to, right?
Right. And don't you think there are some people who might be living right next to one of those blue dots and they think, oh no, I got kidney stones and that was caused by global warming, or my tree blew down, that was caused by global warming, but it didn't even warm where they were, correct?
I think some people know that. You know, I have a few relatives down south and they're a little more skeptical. But I don't know how many people look at what's the trend the last 70 years. Sometimes they just look at what, legacy media says, oh, it's global warming. And, what I had attached to this, if the record cold was like in 32 of the states had record cold below the 1930s, or record warmth below the 1930s. The warmth is just been in a few states. So and I've always had, and this started off when I was trying to study the bird populations, is when you average temperatures together, you obscure all the real dynamics that are important to understand how to make sure that I have a healthy ecosystem. I had, where I was working, people saw a dying vegetation and bird populations were retreating. And they said, oh, this is just what global warming predicted. And I've been looking at it for 10 or 15 years. And I said, really, it has nothing to do with it. It's a drying out that they caused 100 years ago. But what got me looking is that Tahoe City was the closest weather station. And it showed the maximum temperatures were still in the 1930s. And so it had warmed higher than that and the maximum temperature, but minimum temperatures had risen. And so when you average them together, California had a slight rising trend. And they say, oh, rising trend, more evaporation, more dryness. But the thing is, we were out putting nets up to catch birds and mark them so we could follow them at dawn when the minimum temperatures were there. And the minimum temperature was below the dew point. So the minimum temperatures was making the land wetter. And my research assistants would wear rain pants until about 10 o'clock. Because the ground would be so wet from the minimum temperature. And then as the maximum temperature came out around noon, then it was dry. So we average those together and say, oh, look, it's warming. You're ignoring those. And it was the rising minimum temperature that's making them believe that, it was global warming. So you've obscured all this. And let's see if I have something. This is something else this idea of averaging together. There's a number of cities that have data like this. They show that on average, but what you see here is in Atlanta, you see this warming trend. And so you ask, okay, what's happening? How much is it urban heat island? Well, we have satellite data that, and if you look at the one on the right, the red areas are hotter by 12 degrees centigrade than some of the places that are just light yellow. And you say, well, why are these areas so much hotter? And why is it such a big temperature spread? Well, you look at the natural vegetation colors, you see that it's where all the cement and the asphalt of the urbanization is happening, and the areas that still have a lot of vegetation are the cooler areas. Well, you average those together and you get the graph at the top saying, oh, it's this, and then you average all these cities with this warming trend. You say, oh, the global warming. And you got these, I just saw, people gluing their asses to the asphalt or destroying Darwin's grave or throwing tomato juice on Picasso, thinking they're changing stuff. And it blows me away that they've been made that fearful out of bad science, out of bad statistics. And, the old saying, there's lies, damn lies, and statistics. And this is what they do with it, that you can obscure really what's going on.
So another question is that you show all these very complicated cross sections and stuff. Do you think we have any hope of actually modeling the whole climate successfully 50 years from now? We're going to figure out how everything fits together. And to me, it looks like it's almost impossible to model.
I would say it would be impossible to accurately model. It depends on like when I opened with Pakistan, it's in a place where things are so variable because of El Nino, because of how far north the ITC goes, and places with that high variability are going to be a little hard. But you could model and say, well, and get a very general qualification, but to model it exactly, I don't know. How do you get rid of all the how much averaging is going on due to urban heat effects, due to drying the land, due to irrigation, all those different things. So, I think it's tremendously complex. And for people to think that we have any clue really what's happening right now, it's mind-boggling. But there's a lot of gullible people out there.
So I'm just about out of time. I have the sense that you have a lot more content, and maybe we can do it on a separate podcast if you have more. I would love to have you on again.
And if you give me a suggestion of what, I've tried to cover a lot of things. I have a YouTube site. I have about, 40 different YouTubes trying to cover different issues. If there's something you want me to focus on, I'd be glad to do it.
Excellent. Yeah. Any other points you'd like to make now before we wrap this one up?
Keep up the good work. And I didn't congratulate you on Climate the Movie.
Oh, thank you. Yeah.
You've been doing a great job. So it's an honor to be here.
I give Martin Durkin the credit, but I'll pass that on to him. So, all right. Thank you very much. And we'll talk to you next time, Jim Steele. I really appreciate it.
All right. Glad to be here.
Goodbye.